My name is Andreas Rosbacher. I'm a software engineer at Airbnb, working on their infrastructure team, which we call native frameworks. We provide the frameworks that the feature engineers that actually built the app, like the teams that work on hosting or on guest flows, use to actually build the app. But we also sometimes hunt down crazy bugs, and this is like the story. This is kind of like a different thing. It's like it's not even a technical talk. It's a story with a lot of technical content about how we investigated and fixed the bug that was causing half of our crashes. And yeah, it all starts in December of 2018 in this case, and we started to see this weird native crash, and we only saw it on 8.1 and 9.0, not even 8.0, just 8.1. And well, if you're an Android engineer, you're used to seeing stack traces, but this looks very different because it's a native stack trace. And there's these things in there like SK codec, SK image shader. What is it even? Like, I had no idea. And we discussed what could have caused this. We tried to isolate this down to a release, down to a pull request, like the things that you usually do if you're investigating issues like this, and no luck. Like we just couldn't find it. There were not that many crashes, so it was December, like the year-end break started, and yeah, we just one thing we did actually before we finally called the year, went all into our year-end holiday was, well, what you always do if you don't find anything anywhere, you just Google. And there was not much you found. There was like one posting that actually had something from that stack trace. And this is in the Skia discussion Google group. And it said the app randomly crashes on 8.1, and even this was actually hard to find. I had to search for this again to actually make a screenshot for the slides, and it took me like, I think 20 minutes to find it again, and I should actually know how to find it because I found it in the first place. And the Skia team told the reporter that they should just file a bug report, and which they filed, but the problem is they didn't link it here. So I asked, and they luckily they actually replied, and because you just couldn't find this bug report anywhere. And maybe at this point, like, you should explain what Skia is if you never heard of it. Skia is a 2D graphics system, all written in C. And it is the graphics system. It's I think it's open source, but it's mainly made by Google, and it's the graphics subsystem that is used in Android, and I think also in Chrome, to render 2D graphics. So all of the UI that is not rendered by the 3D renderer on the is rendered by Skia. And so at least we know, like, you know, this is something graphics related, I guess. So if you read the ticket that that they opened, that is a little bit it's a little bit over my head, at least like as an Android developer. And there's like all kinds of memory addresses in there and assembly code, and they're talking about suffixes with DOEV and UDF instructions, and I have no idea. We had no idea what that is. And however, the conclusion is pretty interesting. Even though they didn't really share what was the issue and what fixed it, but they're talking about double destruction here. And again, like as an Android developer, that's confusing. Like never heard of anything in Java double destructing, but you know, maybe whatever they're talking about. And they pasted this piece of code here, and without actually saying where did this from. So yeah, now it was time for a winter break, and we did some more research and went into winter break. So we came back in January and looked at this again, and the impact was growing. And we were still investigating, but we couldn't really go anywhere. But by end of January, this has grown to like epic proportions, I would say, because we checked it out and it was 46% of all our crashes. So that's not good. Like if something is 46% of our crashes, like the Airbnb app is really stable. So like something of that size is really like it's a big problem for us. So we struggled again. We did the usual things. We tried to find out how it is introduced. Was it an experiment, a pull request? We just couldn't find anything. So, well, you know, we're all engineers. What do you do if you're completely stuck and you don't know any further? Well, you dissect it. You dissect basically the problem. You look at the code piece for piece, and you're checking what's actually you're trying to find out what's causing this piece by piece. And this is what this presentation about. So, without much ado, like follow me down the rabbit hole of how this one get figured out. And well, let's first start with this piece of code that we saw earlier. It's actually pretty easy to like look this up again on Google to find out where this is from. And this is actually from the shader Java class in Android. And it was changed actually between 8.0 and 8.1 significantly. That would explain like what's happening here, but not really exactly what's happening. So the first thing you notice is there's a hide annotation here in the comments. And what that means is that this method is not the public interface method. Even though it is public, it will not be in the API, which means that you cannot, or you can directly call it from your code, but you shouldn't. And there is also no autocomplete, obviously, to find those things. So still, you know, we're looking. I actually disassembled the code and like see if like any third-party library maybe is calling this in any way, but yeah, it isn't. So if you look at this code, there's two lines that are interesting in here mainly. And the first one is the creation of a native instance here. And then there's the second one, which is this the register native allocation on this as registry on the no image preload holder. The first one, I guess, is pretty clear. It creates some native instance, I guess, which seems to be stored in a long because that's what this thing is returning. And the second one, yeah, we don't know. I don't know what it is. One thing that's pretty obvious here, though, is that this is not thread safe. So if we can totally have a situation where within the same shader, this gets called twice on two different threads, and it potentially creates two native instances, and it potentially also registers the this register native allocation call twice. So yeah, it's not thread safe. Like definitely, like keep that in mind. So yeah. So let's look at this native preload holder, right? So this is the code that is, let me just go back here, in line 11, that's the code that gets called in there. And so this is the registry, this is the newing of the registry. This is also in the shader Java class. And yeah, we can see this, the registry gets defined, it gets the shader class loader, it gets a native finalizer here at the second, and it gets some kind of number. Okay, so now on this one, like let's go back one more time. So we have this registry here now. They get some method and the class loader and some number, and then we call register native allocation on that. So there we go, the numbers, and well, we don't even really have to look at the code of the register here, but we just gonna look at the class, the native allocation registry. So that thing is there to associate native allocations with Java objects. So, and the runtime will arrange for the native allocation to be automatically freed by user-supplied function, and the associated Java object becomes unreachable. Oh, that sounds interesting. So I guess we are registering our native instance of the shader using this. So let's see how this works. So let's look at the actual register native allocation method. And what we can see here, that gets called in the shader that we saw earlier. So what we see here is the referent, and the referent is the Java instance of the shader. And the native pointer just under the red highlighted section is the pointer to the native code. So we can see here, there's like a cleaner thunk is created, then there is a cleaner created, and the cleaner gets the referent, that's the Java object, and the thunk. And the thunk at this point seems to have nothing special about it. But then we set the native pointer to it at the bottom, but only if it's not 0. And 0 seems to be like basically null in this case here, because this is like a reference over to the native code. So again, like there's no checks here, so it's just getting executed. So yeah, if you would call that twice, we would definitely create 2 thunks, 2 cleaners, and let's see what those cleaners and the thunk is doing. Let's first look at the thunk. The thunk is fairly simple if you look at it, because it's basically just a runnable, and you can set the native pointer to, which is just a long, and then when it runs and the pointer is not 0, then it just calls this register native free function, and that is just sorry, it calls the apply free function, which it's down here. It's takes the free function, the native pointer, as references and as attributes, and as you can see by the keyword, this is actually native. So, well, the next thing we do is we're gonna look at some C code, but don't be too afraid. This is actually not very complicated, because you can see again here, like this is the native implementation of that JNI call. You can see here there's the JLong, the free function, and the JLong of the pointer, like the Java long, the 2 Java longs for the pointers for the free function. So what they are basically doing here is, even though it looks so complicated, is they're just casting that free function pointer to a function, and to that free function, and then they're casting the pointer, which is the shader native instance, to the native pointer, and then they just call that function with the native pointer. So yeah, it's basically calling the function reference that we gave it with the native reference as the attribute. That's what it's basically doing. And that function reference we actually provided in the native allocation registry. So so let's see basically what this function that we provided is doing. So this is what that function that we provided in the native allocation registry looks like in C, because it's native again too. And what this is doing is this is calling the native destructor for the shader. This is called Skia. And I think at this point we are like far enough down the rabbit hole to like go back up to like see what's actually going on. So we know what the thunk is doing now. So now we just need to understand what the cleaner is, but yeah, we are basically going back to Java. So we don't even have to look at the code again for the cleaner. But what would happen is that, like, if the object, and that's the shader in our case, gets garbage collected, the cleaner will call the thunk, and the thunk is the runnable that we just looked at, which we just saw that just calls the destructor. And we above saw that this is not thread safe. So we can totally have the same shader instance call, it's the same shader call get native instance multiple times on the different threads and register 2 thunks. And they would both be called if they get GC'd. Here, like it says in the red underlined section here of the documentation, that this is thread safe and ensure that the thunks are only called once. But yes, like every thunk only gets called once, but if you have 2 cleaners and 2 thunks, in each of those cleaners, they will get called multiple times. So the first one would then call into the native code and would actually destruct the native shader. And the next one would be an illegal instruction, because at that pointer location, there will be no free function anymore, because that code was just completely destructed, and it would just crash. So if that's the case, we should be able to reproduce this. We just write a small test app and get and basically call get native instance, which we cannot really call, but no, wink wink, reflection allows you to just call it, and we call it for multiple threads. Make sure that the shader gets garbage collected, and can we actually does that actually cause the same problem? And success. It does. It actually crashes with exactly the same stack trace that we had. We were seeing. We were very happy. Like, finally, we found this bug. It's solved. Awesome, great, but well, not really, because we actually still don't know who's calling this. Like I said before, we already know nobody's actually calling get native instance from our code and from no third-party code. The stack trace has no Airbnb or other code in there. There's just like what we looked at, the SK shader stuff. So no idea. So who's actually calling shader get native instance? And that's the benefit of Android. You can look through all of the code. So just look through the code, and there's quite a few, but nothing really of substance that would actually get called a lot, other than the get native instance call of paint. So the get native instance call of paint has the get native instance call of the shader here. So, but you can see there's another at hide annotation up in there. So this is also hidden API, and again, we don't call it. None of the third-party libraries that we use are calling it. Nothing is calling it. So how does that get called? Well, when you do the same exercise, you search the code and you find that it's called in a few places, but basically it's just the canvas and the draw operations in the canvas that do that, like with that call paint get native instance here, if there is a paint. So if I draw something onto a canvas using the same paint object with a shader on multiple threads, I should be able to reproduce, right? So again, wrote a little test app that would do exactly that, like draw onto canvases on different threads using exactly the same paint object, and make sure that those get garbage collected, and success. Like, it is crashing with exactly the same stack trace. And we're like, great. Now we found it, but well, now we still have to actually find in our own code where we call this. And luckily it was, so no success still, like still searching. Luckily, there were not that many draw operations that we were doing that were done from different threads, because usually, like, you draw on the UI thread, because that's where all the UI is happening. And then, I mean, that's most likely is also the reason why this is not thread safe. And when they actually changed this to in 8.1, they didn't think about to make the thread safe, because nothing in the UI code is thread safe. But it comes down to this bitmap transformation, and this it's a glide transformation. So does anybody see the problem? If you see, you can put it in the chat. And while that, I can maybe explain, obviously transformations, they run on multiple threads, because while Glide is downloading images, multiple images, they do multiple image downloads at the same time, and then after the network is done, they transform them at the same time. So if you do any paint operation in here, it has to be thread safe. And so what we see here, what the problem is there's the paint in here, and that paint is static. That means it's shared by all my transformation objects. which then gets set, the shader gets set on this paint, and then we draw a circle here with that paint, which that is causing it. Like, so we have basically all prerequisites that we were looking for here. We have a paint that is shared between threads, and we have multiple threads drawing using draw functions on canvas and using that paint object to draw on there. And if any of this gets garbage collected, then yeah, this can totally happen. So we changed it to a separate paint, which literally meant just removing the static in this case. And let me actually go back here. Like, I forgot to say one thing, which is this is wrong anyway. This would have been wrong anyway, and it actually should have been caught by code review. Not for this bug, because this is a very specific bug, and we cannot expect anybody during code review catching this. But what you're seeing here is that this paint is actually shared between multiple transformations. That is not a good idea. So because that means like we don't even know what paint we are using when we're drawing to this canvas. So this should have been caught earlier. It wasn't, and it was not creating the issue that it maybe also created, because potentially any which of those drawings are wrong. And for example, this in the Airbnb app was used to draw the little circle icons, like you basically can see right now in the chat here, like everywhere this was in the Airbnb app, this was used. So every time you would scroll through like lists with a lot of circle icons, this was potentially happening. So we changed it, and that was actually it, success. Like this time we actually really fixed it. The issues went down to 0 in newer versions after we fixed this. And yeah, this is the story of like how we fixed like an issue that was half the crash rate, and it was caused by like a tiny little bug, and it had no reference of any of our code in the stack trace. What's interesting though is if you, with all the stuff that I just talked about and the stuff that you hopefully learned, look at the stack trace on the first slide. Actually, now it looks, you could basically see what's happening here, because what's happening is that a thread is run, and that thread is running the reference queue and queue pending, that's the garbage collection. The garbage collection calls the cleaner. The cleaner calls our native allocation registry thunk run, and that is calling into the native Skia code, which is calling the destructor. And that is failing here at this point, because that's the second one, and it's just breaking. It's just broken. Okay, that was my talk. So thank you very much, and check out where you do your paints and how you share them.